morning, everybody. So I'm a bit late because I am a bit having some medical problem. Yesterday we discussed about a fin that is infinitely long. If you have a very long fin, then what is the temperature distribution that we have derived? And this is the temperature distribution T minus TA. The temperature inside the fin T at a distance x minus T ambient is equal to T base. This is the temperature at the base minus T ambient into e to the power minus mx. This is the temperature distribution inside the fin. By inside the fin, I mean along the length of the fin. And at any cross section at a distance x, we assume that the temperature is same. It is only varying with x. Now, this is for a very long fin. And we have derived the temperature distribution. Also, we have derived an expression for heat loss from the fin. The rate of heat loss is given by Q dot fin. We have derived this as equal to Q dot fin is equal to square root of HPKA into TB minus TA. And also, we have derived two performance parameters known as fin effectiveness. What is fin effectiveness? That if we use a fin, what is the rate of heat transfer divided by if there were no fin is called Q dot unfilled. So ratio of Q dot fin by Q dot unfilled. This ratio is called the effectiveness. And naturally what we expect is that if we use a fin, the heat transfer rate from the fin should be greater than if there were no fin. When there were no fin, whatever the heat transfer, in presence of the fin, we expect that the heat transfer will be more. So this thing should be greater than this. The numerator Q dot fin should be greater than the denominator Q dot unfilled, so that the effectiveness value should be greater than 1. But this is our expectation. If we design a fin in an inappropriate situation, then it may not happen. Or if we, even in an appropriate situation, if we design a bad fin, then also it may not happen. By appropriate situation, we mean that if the value of H is already very high, in the situation, in the environment where the value of H is very high, there is every possibility that if we attach a fin, the effectiveness for the fin may be less than 1. That means the heat transfer rate from the fin may be less than when there were no fin. And that is quite evident from this expression that the effectiveness is inversely proportional to H. So the larger the value of H, the lesser will be the value of effectiveness. So for a very high value of H, situation where the value of H is very high, there is a possibility that effectiveness may be less than 1. So that is what I mean by an inappropriate situation. And that is why in situation where you have already a very high value of H, you should not try to attempt use a fin. And when H value can be quite high, particularly in situations where we have a boiling or a condensation. In situations where change of a liquid, then the value of H can be quite high. If we have a fluid where the phase change is taking place, for example, if you have a vapor which is condensing, the value of H can be of the order of 10 to the power 5. Or if we have a liquid which is boiling, then also we can have a very high value of H. So in those types of situations, we should be very careful before we attempt to design a fin for those type of things. We may not require any fin at all in those situations. But in situations where the value of H is very low, we may require to introduce fins. We may require to design fins. The value of H may be as low as 10, 20, something like that, or 100. In those situations where the value of H is less, much less, then use of a fin may lead to a high effectiveness, and what we require is that the value of effectiveness should be at least greater than 1, much greater than 1 is desirable. And if it is equal to 1, then the fin has no effect. Unnecessarily, there is no point attaching a fin. We cannot improve the heat transfer. And the worst thing can be that when the effectiveness may go down, then it is a detrimental fin. And that is what I said is that one of the primary reasons may be where the value of H is very high. That is why if you see carefully now onwards, in many situations, you may have a separating wall which separates two different fluids on two sides of the wall. Suppose we have a wall, the wall may be the wall of a pipe, the wall may be wall of a tube, the wall may be a plain wall. In all these cases, if the wall is separating two fluids on two sides, one hot fluid, one cold fluid on two sides of the wall, then there will be heat transfer from the side of the hot fluid towards the side of the cold fluid. There will be heat exchange. Now, if we want to promote this heat transfer, then what we can do is that we can think of attaching the fin. Now, question is, if we have two different fluids on two different sides, having two different values of H, H1 and H2, what you will see is that the fins are attached many a times on one side, not on both the sides. And which side the fins are attached? You see that the side where there is a gaseous medium, you'll see that most of the time the fin is attached on that side, because gases normally offer a very low value of H, whereas liquids can provide high value of H. You'll see that mostly if you have a wall that is separating a liquid and a vapor, you see that a liquid and a gas or vapor, you see that the fins are attached on the gas side, because on the gas side the value of H is very low. And that is why if you see a car radiator, the example that you have taken at the very beginning, this is how the radiator of a car looks like. There are a series of vertically oriented tubes, and on the surrounding these tubes, we have a stack of plates. These plates, they act as fins. Now, what we see is that what they have shown is that inside the tubes are shaped elliptic to minimize the pressure drop and also to provide more surface area. It has been made elliptic, but as you make this surface area more, it should be oriented in such a way that the pressure drop is less. If you imagine the tubes are oriented not in this along this direction, but just perpendicular to this, then what will happen when the gas flows over this thing, over the tubes, which has a major axis across the flow direction, you see that there will be more pressure drop. But if we have the major axis along the flow direction, what we can expect naturally is that the pressure drop will be less. So that is why it is oriented like this. Now what I am saying is that what you see that inside this tube you have the liquid flow, outside this tube you have the gas flow, maybe air flow. And what you see is that the fins are not attached inside the wall but outside the wall, because there is a gas flow, the value of H is very less. That is why we attach fin on the gas side. Here also what you see is that inside the tubes you have the liquid flow, so you don't attach fins inside, but outside the tubes you have the gas flow. You attach fins on the gas side, because on that side generally the value of H is less. Now we may have a situation where please
recording
time in পরে করছি, একটু পরে বলো. What I am saying is that suppose you have a situation where you may have a very, for example, suppose you have a gas flow inside and liquid flow outside. Then we will be constrained to use fins on the inside and not on the outside. But before doing that thing, what we can think of is to alter the passage of the two fluids. That is, if we have a situation like this, that what we should try to do is not to allow the gas to flow inside, because if gas is to flow inside, then we may be required to use fins inside, and construction of the flow of the fin inside is somewhat difficult. That is why what we should think of is, when we are designing this thing, that which fluid will be flowing on which side. So if we have this type of a situation, we should try to keep the flow of the gas on the outside and flow of the liquid on the inside, and on the outside then you provide a fin. Now this will be required for another situation. Suppose, let me tell this thing and then we'll go, okay, I'll come back to this thing later on again. We have discussed about this effectiveness. Another thing that we derive is, once we ensure that the effectiveness is greater than 1 for a particular fin, then the question is, okay, the fin is effective when effectiveness is greater than 1, but whatever fin we design, could we design a much better fin, or how best the fin can be? How far away we are from the best possible fin? That is the second question of concern, and that question is being answered by another performance parameter known as fin efficiency. Apart from fin effectiveness, we require to also consider another parameter, performance parameter, called fin efficiency. That fin efficiency is the ratio of the heat transfer from the fin divided by the heat transfer from an ideal fin, the best possible fin, or divided by the heat transfer from a fin that can give us the maximum possible heat transfer. Okay, so that is what we express in terms of a quantity known as fin efficiency. What is fin efficiency? That is the rate of heat transfer from the fin divided by the maximum possible heat transfer from a fin that we call it as the ideal fin, or which, if the conductivity approaches to infinity, then the temperature drop throughout the fin will be negligible, so that the temperature throughout the length of the fin will be to the temperature at the base of the fin. Let me repeat once again, that what is the maximum possible heat transfer from the fin? That is, for a fin where the temperature drop along the length of the fin is negligible, where the fin temperature remains uniformly heated throughout the length of the fin, and that temperature is equal to the temperature at the base of the fin, where the temperature is maximum. In general, what happens is that along the length of the fin, the temperature decreases from TB, maximum value TB at the base of the fin, and then as we move out from the base of the fin, you see that there is a temperature drop that is given by that expression, that T minus T ambient is equal to TB minus T ambient into e to the power minus mx. That is the temperature distribution. Now if you plot this thing, you see that at x equal to 0, it will be equal to what? At x equal to 0, right hand side it will be TB minus T ambient. So T at x equal to 0 will be equal to TB. That is also expected from the boundary condition at x equal to 0. And as we have a higher and higher value of x, that is, as we move away from the base, but the x value increases, then what we will see is that this value will be smaller and smaller, because this is nothing but 1 by e to the power mx. So as x increases, e to the power mx will be larger and larger. So this value 1 by mx will be smaller and smaller. So T will be decreasing progressively from TB to a lower value. So the heat transfer, the temperature distribution will be exponentially decreasing as we move away from the base of the fin. I should have drawn one temperature distribution over here. The thing will be something like this. Suppose we have a x-axis that on which we plot, we have an y-axis on which we plot the temperature, and we have the x-axis that indicates the distance from the base of the fin. So this is the x-axis, is the distance from the base of the fin, is the x, and on this we have the temperature. And how it will look like is the I don't know how to plots. No. The temperature will be something like this. To make an exponential graph. The temperature distribution will be something like this. And what is this value? This is equal to TB. At x equal to 0, this is x equal to 0, T will be equal to TB. It's TB. And as you move away, it will be approaching to a value of, as you move away, it will be approaching to a value of T ambient. T ambient is something like this. This is our T ambient. Okay, so the temperature falls at x equal to 0. That x equal to 0 point is called the fin base or base of the fin. At the fin base, the temperature is TB, the base temperature. Then as we move away from the base and as we move towards the tip of the fin, the temperature drops and it approaches to the ambient temperature. Ideally, this will be meeting at infinity. But what you see for all practical purpose, after some distance, the temperature difference between the temperature of the fin and the ambient temperature that decreases progressively, and after some distance, the effective temperature difference is not enough to cause enough amount of convective heat loss. That is why normally fins should not be made much longer. They should be provided enough length up to a distance where the temperature difference is enough, and up to a distance where the heat transfer will be enough. And beyond that, the length of the fin will be useless. So you should know how long you should make a fin. And but I am telling, this is for a particular value of m. Now, if we increase the value of m, suppose this value of m is equal to some value, say 0.5. If we make the value of m equal to 0.6, then which way it will change? Can somebody tell? Can we have another such thing? We can have another such thing where this is like this. We can have another such thing where we can have this. Can somebody tell that what is the difference between this graph and this graph and this graph? And for this is for a particular value of m1, m2, m3. Can you tell which one is for a greater value of m and which one is for a lesser value of m? I'm giving a Q that
If we have less value of m, then the slope will be greater.
what is M consisting of? M is equal to square root of PH by KA. Now
Hmm.
think of a situation that H is high. Then M is equal to square root of H into P. Suppose H is very high. Other things are same. H is very high. Then your M will be high. And
Yes.
if H is very high, then there will be a greater amount of cooling of the film. So the temperature will drop rapidly. So
Hmm.
a large value of M means where the temperature drop will be rapid. But if you have a low value of H, then value of M will be less. And if the value of H is very less, that means there is a slower rate of heat loss from the length of the fin. So the temperature drop will be slower, something like that. So we can say this is a higher value of, this is corresponding to a higher value of M than a somewhat smaller value of M, smaller value of M. We think of another situation where we have a high value of conductivity. Now, see, the heat transfer rate can be achieved even when, if you have a very high value of conductivity, then even with a very small value of dTdx, you can have enough heat transfer. So when you go for a higher and higher conductivity, your temperature gradient at the fin base will be smaller and smaller. You can think of a situation where the conductivity is approaching towards infinity. Then even with a smaller temperature drop, even with a smaller temperature gradient, you can have a high amount of heat transfer. So the ideal fin is one. What we said is that the ideal fin is one where the conductivity approaches to infinity, so the temperature gradient at the fin base will be approaching to zero. And if the temperature gradient is approaching to zero, then you will have virtually no temperature drop along the length of the fin. So the ideal fin is one where the temperature variation will be something like this. The temperature variation for an ideal fin. So what will happen? Throughout the length of the fin, you have the same value of temperature difference, which is the cause for convective heat loss. So for this case, the heat loss will be the maximum. That is for the case of the ideal fin, that there is no temperature drop. The temperature is uniform over the length of the fin. The heat transfer or heat loss from the fin will be maximum because the maximum temperature difference remains constant over the length of the fin, and throughout the length of the fin, same rate of heat transfer will take place from the fin to the ambient. So that is the maximum possible. You cannot have more than this. You cannot have a fin base, or you cannot have a temperature distribution which is losing a, which is, you cannot imagine a fin where the heat loss is taking place and the temperature is going up. So that is the limit of heat exchange from the heated fin to a colder environment. So the maximum possible scenario is where you have a fin where the temperature remains uniform throughout the length of the fin, and that can happen for a fin where the conductivity approaches to infinity. And when conductivity approaches to infinity, what is the value of M? M becomes equal to 0. Well, M is equal to square root of pH by Ka. So because K is on the denominator, so M will approach to 0 when K approaches to infinity. So this is for the ideal fin. This is the temperature distribution where the M is equal to 0. This for M is equal to 0. Okay. And for all other fins, the value of an M cannot be negative. M minimum value of M is 0, which is for the case of ideal fin and when the K approaches to infinity. And for all other real life fins, the value of K will be finite and the value of M will be something greater than 0. So this is the direction of what you call so when your M is increasing, you will have we will have a situation where this is M is increasing. This is M increasing. This M is increasing, larger value of M. Okay. If you have any question, you can ask me. Otherwise, I'll move forward. Any doubt about anything? You can ask me. Otherwise,
No, sir.
the approaches to infinity. The symbol is required. Anybody having any doubt, please. Otherwise, সেটা পরে এটাকে ডিসপার্টাইল একটা ইনফিনিটি সিম্বল এখানে লাগিয়ে দিতে হবে। So this is the temperature distribution along the length of the field. So you can take it and paste it over here. Something like this. ইনফিনিটি লাগাতে হবে, সে পরে দিয়ে দেবো। ঠিক আছে তো? Now let us move forward for another type of boundary condition. You have class in the next period. Do you have class at 11 onward? Hello?
সিআররা প্লিজ রেসপন্স কর, তোদের কোনো ক্লাস থাকলে স্যারকে বল।
10 মিনিট। You have
No, sir. You can continue.
Okay. Now, let me tell another thing, then I will move forward for the next cases. This is for one type of boundary condition that is called a lock field. Then we will discuss about a convection from the type 2 is where type 2 boundary condition is when there is significant amount of convection from the fin tip. And when this will happen? This will happen when the tip temperature is substantially high, and when that will happen when the length of the fin is not very long. As you can see, here, as you move away from the base, the tip temperature is approaching towards the ambient temperature. So there is very negligible amount of heat loss in this region of the fin where the temperature difference between the fin and the ambient temperature is becoming very small. It is narrowing down the temperature difference between the fin temperature and the ambient temperature. The difference is narrowing down. So this part of the fin is not so much effective. So maybe it would have been better if you could provide a smaller length of the fin. Whereas for this fin, even here the temperature difference is significant. So for this fin, we can have so much of length. Now what I am saying is that if we have a small length of the fin, then if we have a length of the fin that is much smaller, then what will happen? The tip temperature also will be quite high compared to the ambient temperature. So there will be significant amount of temperature difference between the fin tip and the ambient. And moreover, if the length is small, then the surface area of the side surface area will be comparable to the tip area. So area is comparable and temperature difference is quite high. So the heat loss from the fin tip may not be negligible compared to the heat loss from the rest of the surfaces. So then we have to take the convection from the fin tip. That is the second type of boundary condition that we will consider. And there is another type of fin boundary condition that we have mentioned about is the fin tip is insulated. Number one, we have discussed so far, we have completed the discussion for heat transfer from a very long fin. Second is, if we have a significant amount of convection from the fin tip, that what will be the corresponding equations and other things like. And the third thing that we'll discuss is for an insulated tip fin. And now question may be that why at all will consider this type of a thing where the fin tip is insulated, because the fins are attached for promoting heat transfer. Then why at all will insulate the tip of the fin? Is there a need for taking an extra step for insulating the tip of the fin? It is not like that. But at the same time, it can happen even for a small length of the fin. It will happen very frequently, not deliberately, but by natural situation. Let me explain when it will happen, and this will be a very frequent case compared to long fin case. It may be quite a frequently appearing case. Why at all it can happen? And I would ask you to find out an explanation for this thing, not from yourself, but you just try to see when this type of situation can arise, and you try to see in different books and try to come up with an explanation that why at all you should take the tip of the fin insulated. Okay, what I thought is that I will try to explain to you why at all we should take a insulated tip fin, and why I am telling that this is the most frequently occurring type of thing that can happen. I am keeping this for today, but try to find out an explanation from some book or somewhere, and if you find an explanation, tell it to me, otherwise I will put my explanation. So today what I will do is that I will take now the second case, that is the convection from the fin tip. So what will be the boundary condition? That at x equal to 0, t is equal to tb. This is common for all cases I have said. Then for the long fin, x equal to 0, t is equal to tb. For the second case, when there is convection from fin tip, there is t is equal to tb at x equal to 0. And even for an insulated tip fin at x equal to 0, t is equal to tb. Now, this is one boundary condition. This is the second order differential equation. So we require another boundary condition. Let me make the recording on. Today we are going to discuss about another type of boundary condition where there is convection from the tip of the fin. हाँ बोलो हाँ बोलो हाँ Actually, all kinds of things are happening. Now today we'll discuss about the convection from fin tip, and at the tip then the boundary condition will be minus at x equal to L. There is the length of the fin, or you can say that is at the tip of the fin x equal to L. The boundary condition will be minus k into dt dx will be equal to h into t minus t ambient. So why you have taken a different value of h is because what you will do subsequently is that whatever thing we develop in that, if we put h equal to 0, then it will represent an adiabatic field or a field where the tip is insulated. That is why we have taken this value h different from the rest of the value of h. Rest of the field we will consider a convection coefficient given by h, and at the fin tip we have taken a different convection coefficient, so that if we put h over here, h equal to 0, it will lead to the derivation for a insulated tip field, but still h will remain non-zero. And subsequently, when you derive the equation for a value of he with he, and once we derive the equation, there also we can set h equal to h. So we have the choice to make h equal to h and h equal to 0, and h different from h. All these things are possible. That is why you have taken at the tip a different distinct value of h from the rest of the field. Now what we will do is that, you see, theta, this is a very general solution for this governing equation, theta equal to c1 e to the power minus mx plus c2 into e to the power mx. Now what we can do at x equal to 0, if we put theta equal to theta b, that is the base of the field. At x equal to 0, theta equal to theta b. So it becomes theta b is equal to c1, this becomes equal to 1. X equal to 0, this thing is 1 and this thing is 1. So theta b is equal to c1 plus c2. That is one equation in terms of c1 and c2, and we will substitute another boundary condition, that is at x equal to L, it is minus k into dt dx equal to he into tv, he into t minus t ambient. This boundary condition will put at x equal to L. Then what happens? Then how to do it? If theta equal to c1 into e to the power minus mx plus c2 into e to the power mx, then what is d theta dx? Then d theta dx will be equal to c1 into minus m into e to the power minus mx plus c2 into plus m into e to the power mx. So when x equal to L, d theta dx equal to how much? It will be equal to c1 into minus m e to the power minus ml plus c2 e into m into e to the power ml. So here we'll put this thing for d theta dx at x equal to L, and what will be the value? This is theta. So what is the value of theta? That is equal to C1 e to the power minus ml plus C2 into e to the power ml. We'll put this into this second boundary condition, and we'll get another equation in terms of C1 and C2. So we have from the first boundary condition, that is at x equal to 0, theta equal to theta b, we'll get one relation between C1 and C2, that is C1 plus C2 equal to theta b, and we'll use the second boundary condition as minus k into d theta dx at x equal to L is equal to he into theta at x equal to L. We'll get another boundary condition. With the help of that, we'll get another relation between C1 and C2, and then we'll have to solve it for C1 and C2. We'll solve it for C1 and C2 to get the solution for C1 and C2. Today, I'd like to stop over here. So we'll have two equations for C1 and C2. Solve it. This I'll do in the next class. Meantime, if you want, you can proceed with yourself. And have I circulated this PDF with you? Have I circulated this PDF with you? Okay. What I'm doing, what do you prefer? You circulate this thing with you?
Yes, sir.
I remember that I have given this entire thing. I have never circulated anything with you. Did I circulate any PDF with you?
Yes, sir. Yes, sir.
Yes,
I
yes.
think that PDF, because this is a running note that I am having. I think that PDF that I have given, you can look at it. We shall come back to you. What about tomorrow? Do you have any class tomorrow? Any empty space? Because we missed certain classes, so that we can finish this thing by this week itself.